Welcome to The Explainer. Today, we're breaking down how computers learn to do something remarkably human, put things into categories.
You know, it really does feel like magic sometimes, doesn't it? But the answer lies in a super powerful technique from the world of predictive analytics called classification.
So what are we really doing here? We're basically building a little decision-making function. We feed it a bunch of information, what we call features, and it predicts which group or class that thing belongs to.
Okay, to make this really hit home, let's walk through an example from finance. Imagine a bank. They want to know ahead of time if a customer is going to default on their credit card payments. And they're trying to predict this using just two simple pieces of information: the customer's income and their current credit card balance.
So, where do you start with a problem like this? Well, the most intuitive idea, the one that probably just popped into your head, is to just draw a straight line to separate the people who default from those who don't. This approach has a name. It's called linear regression.
And on the surface, this seems super simple, right? We just turn our outcomes into numbers, fit a line to the data points, and then use a simple rule. If the prediction is over 0.5, we'll call it a default. But here's the catch, and it's a big one. This simple method runs headfirst into a massive logical problem.
Okay, here's the absolute core of the issue. A straight line doesn't have any boundaries. It can just keep going up or down, forever. This means our model could spit out something completely absurd, like saying there's a 115% chance someone will default. Or even weirder, a negative 10% chance. In the real world, that's just nonsense. Probabilities have to live between 0 and 1. That's it.
And believe me, this gets way messier when you have more than two choices. Think about a hospital trying to classify a patient's emergency condition. Using a straight line would basically force these distinct medical events onto a number line, suggesting a drug overdose is somehow in between a stroke and a seizure. That makes absolutely no medical sense.
So yeah, clearly a straight line is just the wrong tool for this job. We need something smarter, more elegant. And that brings us to a technique called logistic regression. So instead of that clumsy straight line, logistic regression uses this really clever S-shaped curve. And the beauty of this curve is that by its very nature, its math is designed to be squeezed between 0 and 1. It literally cannot go any higher or lower, which makes it absolutely perfect for modeling probabilities. It just elegantly solves our problem. But you might be wondering, how does the model find the perfect S-curve for our specific data? I mean, there are infinite possible S-curves, right? It doesn't just guess. It uses a really brilliant method called maximum likelihood estimation, or MLE.
Now that sounds pretty dense, but the idea is actually very intuitive. Imagine trying on a bunch of different S-curves. For each one, the model asks, if this was the true curve, how likely is it that I would have seen the actual data I have in front of me? It does that for all the curves and then just picks the single one that makes our data look the most, well, likely.
Okay, so logistic regression is a fantastic tool, but it's not the only tool in the toolbox. It's much better to think of these different classification models as a whole team of specialists, where each one has a unique skill set and a totally different way of looking at the problem.
And this team is basically split into two camps with two different philosophies. First, you have discriminative models, like the logistic regression we just met. They are obsessed with finding the boundary, that perfect dividing line between the groups. Then you have generative models. They do something totally different. They try to learn the story of each group, what a defaulter looks like, what a non-defaulter looks like, and then they classify a new person based on which story they fit into best.
So, let's meet a couple of these key specialists. You've got LDA, which is a generative model that's really stable and solid, especially when your groups are pretty far apart. But it does make one big assumption, that your data follows a nice, clean bell curve. Then there's Naive. This one's the speed demon. It's incredibly fast because it makes a naive, and usually wrong, assumption that all your features are totally independent of each other. But here's the crazy part. Even with that assumption, it often works incredibly well. All right, so we've picked our model, we've trained it on the data. But how do we know if it's any good? We need a scorecard. And trust me, it's not as simple as just counting up how many answers it got right.
And this right here is that scorecard. It's called a confusion matrix, and it's the standard tool for this job. It's a simple little table that compares what the model predicted to what actually happened. It shows us where we were right, our true negatives and true positives, but more importantly, it shines a spotlight on our mistakes, the false positives and the false negatives.
So let's look at our credit default model. At first glance, the overall error rate looks pretty low.
You might think we did a great job, but when you dig into this matrix, you find a complete disaster. Our model missed 252 of the 333 people who actually defaulted. That's a false negative rate of over 75%. We failed to identify the very people the bank was most worried about finding.
And this brings us right to the heart of how you evaluate any classification model. You have to ask the critical question, which type of error is more costly? For the bank, wrongly flagging a good customer is an annoyance. But telling a risky customer they're safe? That could lead to a huge financial loss. The real-world consequences are everything.
So at the end of the day, successful classification isn't just about finding an algorithm that gets the most answers right. It's about deeply understanding the problem you're trying to solve, picking the right tool whose assumptions fit your data, and then, most importantly, measuring success based on the real-world consequences of your errors.
And that leaves us with a final thought to take with you. When the stakes are life and death, like in a medical diagnosis, the choice between these two types of errors is profound. Is it worse to tell a healthy person they might have cancer, or to tell a sick person that they're fine? The math can build the model, but only our human judgment can decide which mistakes we are and are not willing to live with.